Nice. So, yes, everyone maybe saw on Slack, the plan today's Ramy was going to present some slides. And we can kind of discuss ideas around that. And then if there's time at the end, we can just kind of open up to more general brainstorming. Um,
Okay.
yeah, I guess whenever you're ready, Ramy. And do you want us to ask questions from the start, or would you prefer us to kind of wait for a bit?
I think it's fine. Yeah, go ahead, ask questions. A
Okay,
lot of this is mostly um, me not being sure that my understanding is correct, and I think the best way is to just have this interactive and as
yeah,
soon as I make a mistake, just let me know that this is not how we think about it. And
cool.
all right. Um, can you see my screen?
Yep.
Yes.
Okay, so I'm going to be talking about modeling object behaviors, and I'm going to be proposing a slightly different way of looking at it. It's the same, I'm going to be starting from the same current theory that we have, but it's going to change in some details. And yeah, I'm just hoping to have some discussions on this. So so let's start with the current theory. Right now, we have movements that are coming from the thalamus, relayed by the thalamus, and from magnocellular pathways, some of those cells have larger spatial receptive fields that are going to uh, represent the sensory location or the sensor movement. Excuse me. So something like this, you're looking at a stapler and you move your eye. But there is also another signal that is coming from magnocellular pathway that also has smaller receptive fields, and it's just representing the patch movement. So you're still looking at the same location, you're not moving your eye, but the object itself is changing or it's morphing in some way. Could be also color changing or
Well,
yeah.
that's why you have patch movement. I think the last we talked about it, we were opening that up to basically change. It's something's changing at that point, not necessarily moving. Moving would be a big part of it. In the stapler, it would be moving, but like the light on the traffic light's not moving, but it's changing.
Right. Okay. So so something changing there, but it's not related.
And just to be clear, it's not that the patch is movement, it's the observed feature that what the patch is observing, the feature is changing
Feature
and the
change.
feature is moving, right? We're not talking about the patch moving, right?
Okay.
You agree with that?
Yeah, I agree. Yes. Because we don't really we can't really observe the movement of the patch. We just can observe that.
Right. And that's not the important thing. The important thing is that the object itself is changing.
Right. Yeah. Okay. And the features themselves are going into they're coming from a different pathway from the parvocellular pathway. And they're not representing change, they're representing the actual features that we're looking at. So in order to build models, the current theory is that we have two reference frames, and we have an object reference frame. This is both of these reference frames are representing locations in physical 3D space, and they are tying or they're learning. One of them is learning the features at these locations, and the other one is learning movements at these locations, and they are both synced, and they're both using the sensor movement to know where we are. And the object model and the behavior model, they're learned. They're basically this is knowledge embedded in the associative connections between the features and the locations and the movement of the locations. So the model itself is in the associative connections. I hope I got that right.
Right.
This part.
But again, I'm going to be precise, Rami, in the language. They don't represent, although they are, every location you're observing has some physical location. The two reference frames are representing, on the left is representing the space of the object, the set of features, the static feature. Well, excuse me, one on the right is representing the set of static features,
Mhm.
and the one on the left is representing the space of the changing of the features. And although they are co-aligned in physical space, they do not represent physical space in the sense that they would re-anchor on different objects or different behaviors. So it's not like for someone who's new to this, you wouldn't want to say these reference frames are physical space. They're not in some egocentric space, or they're in the space of an object, or in the one case, or the space of the extent of the changing features in the other one. It's just
Okay.
subtle language, but it's important I find it important to keep using the correct language on those.
Yeah, and I think this is the part that I may have some confusion on, and
Or maybe you're proposing something different. Okay, so in which case I should be quiet.
it's
You did say current theory. So,
well, I'm not proposing that we're going to change the theory. I'm just saying that
okay.
this is where I'm starting from.
Yeah, it's a hard, if you haven't spent a lot of time with grid cells, it's a hard concept. But they're really, they anchor, right? And so when they anchor, each time you're anchoring for a specific object or a specific thing. And so they're anchoring for the specific object, for the stapler in this case, the one on the right, and then on the one on the left, a similar set of grid cell modules is anchoring for the movement, the changes, and that's basically all you can say about it,
Yeah. Okay. Well, so I find it useful that we dig a little bit deeper into the reference frames, because maybe this is the part where I need to uh, be better understand. So I'm just going to talk a little bit about reference frames so that I make sure that I have the same understanding. So my understanding is that a reference frame is some sort of coordinate system. It's a metric coordinate system, I think, as you usually refer to, Jeff. It doesn't have an origin, so it anchors to different objects, but it does not really have an origin. They're not related the objects are not related in space relative to each other. So what I'm going to show next is not the right way of showing what the anchoring is, because we don't really go in space and look at these objects like that. I understand that the representation of the location itself changes, or when it re-anchors to something, it's like it's reinitializing to, or it's initializing to that space, so that there would be no conflict between those locations. But but we're not really like moving in space looking for these objects like that. But this is like the closest thing I could animate.
In the way it's implemented in Monty is not the way it's implemented in the brain, my understanding. In the brain, we have these grid cell modules, and they end up creating a sparse distributed representation space. But in Monty, we're not doing that. My understanding, we're using more traditional Cartesian coordinates, but we prepend a sort of a class modifier, where we essentially just put this in some other space. So when we talk about the reference frames, we really are talking about two different implementations, and we have to be careful, because I'll be thinking about the brain's way, and you might be thinking about Monty's way, and they're not the same. Although I've been assured multiple times that it works just fine, that they're different, but we should keep in fact they're really quite different. The way you show the picture there, I think, more corresponds to the way Monty does it. It doesn't really correspond to the way grid cells do it.
Yeah. Like I said, they're not related in space like that. And once we re-anchor, it's not like we're moving to a different space, but it's just, I understand that the representation itself, the grid cells changes. It's like all of these are like randomized and initialized in a way such that it gives us a new space to represent the new object.
Yeah, I think the important thing is that the location encodings aren't shared. So a location STR on the coffee mug is unique to that location on that coffee mug, and we won't get that same location on a different object. So I guess generally how you put it on the slide, like the definition that a reference frame is a coordinate system without an origin, I would say it wouldn't be right. It's more like grid cells don't really have an origin in the way that they encode space. But usually how people think about reference frames is that they do have an origin, and that's why we have an origin in Monty, because we're using Cartesian coordinates, and that coordinate space requires defining an origin. But then we kind of use that shorthand, like Jeff mentioned, that we kind of prepend like a class modifier, so that every object has its own location space, and it's not like zero, coordinates 0, 1, 0 exist in two objects.
Okay.
It's kind of weird in grid cell space. It's not only don't have an origin, the potential size of grid cell space is so enormous, like, size of the universe, bigger type of thing, that, once you anchor, you can path integrate around the set of points, but they're all SDRs. And it's not like X, Y, Z. But you'll never ever travel far enough to get to another object's part of the world. You know what I'm saying? Whereas we think about Cartesian coordinates, you can say, oh, I'm going to put the reference frame for this particular object up here in this distant corner and another one over in this distant corner or something like that. But it's not like that in brains. It's really kind of a very clever but totally different way of doing it. But I'm not sure if that's going to impact what you're saying here. I'm just pointing out the difference.
Okay. Yeah, thanks. And this same thing that Vivian was talking about, that the locations are unique to the object. So whatever location we define with respect to the anchor object is not going to be shared by the other objects. But my understanding is also that the movements are shared, that the
Right.
meaning of movement is shared. So
Right.
okay,
Right.
so go right or go left or whatever. This is going to move the locations the same way.
They both will path integrate properly.
Right. Okay.
Right.
Okay, so I'm just gonna go now into the more speculative parts. This first part is the same. We already know that this is how we learn features at locations. We just look at we're getting some patch features, and we move through the object's reference frame and learn the associations like that on an object. But
these are nice animations. How did you make them?
Oh, I guess I've learned some transitions in PowerPoint.
It's all done in PowerPoint.
This is with
Wow.
PowerPoint?
Wow.
Yeah.
So is that like occluded? Is there a stapler moving rather than a window moving in that case?
This is
Like a stapler object moving behind a window?
yeah, this is what I'm doing. I'm cropping it and I just move
Yeah, okay.
position.
Nice.
Wow.
Yeah,
That's
so
pretty
more.
impressive.
That's-
Again, I don't want to be too nitpicky here, but the latest thinking we've had, latest thinking I've had, is if we accept this idea that the center surround receptive field, then you wouldn't have an input that's all black. The bottom dot there, or the bottom, it's half white, half black. That makes a lot of sense.
Mhm.
But from the biology point of view, not from Bonnie's point of view, from the biology point of view, it's not clear that you'd have any input at all when you're looking at a solid black area or solid anything. It's really what the features are always going to be non-uniformities of some sort. And so, when we see a red circle, we're really actually only learning the edges of the red circle, and everything else is implied in between. So it's just a subtle difference, worth
Yeah.
mentioning, perhaps.
And this is why we're always saying it's edges at locations or orientations.
Oh, yeah, I've come to think of it really as non-uniformities. It's just like, because that's what center surround receptive fields do. They just, if you give them any kind of uniform pattern, they won't respond. But if you give them any kind of non-uniform pattern over their receptive field area, they will respond somehow. Yeah.
It's
But
kind of
again,
interesting thinking about that in terms of 3D objects, because like if you talk about images, it's kind of easy to picture how, yeah, like a circle, it's more efficient to not try and like learn all the points in the middle of the circle because it's all the same stuff. You're just going to learn the edges. But what does it mean when we have a 3D object where uh, essentially every surface is in some sense as meaningful? I mean,
well,
I guess you could have
I
kind of
don't
like
know.
3D corners and stuff like that
Right.
might be more
Well,
interesting.
it's pretty speculative, but I mean, if you follow the logic, then you say, well, if I have a flat surface, that
Yeah,
would be uniform. But if I have a curved surface, that's not uniform.
Hmm.
And
yeah,
there's some information there, you know. It's not all the same. If I can detect that curvature, then it's non-uniform. So in that case, you might, you get to the top surface of a table, you wouldn't learn all the points on the table if, you don't have to touch all the surfaces on the table.
yeah, yeah. And maybe
I
even
don't know.
if the curvature is kind of constant, then that can also be kind of
Maybe, right.
approximated.
Yeah, I don't think we understand it well enough, but yeah.
But yeah, it's hard to kind of map on like edge detection as it happens with a 2D projection onto 3D
Well,
features,
I think
which is like
clearly
currently what Monty uses. Or like
anytime,
I'm not saying sorry, when I say it's hard to map on, I'm not saying it doesn't apply or like it doesn't make sense. It's more just uh like we've talked about like how we might get like 3D features from and like where they might emerge I guess a couple months ago. But I think it's still like the classic neuroscience view of what like the thalamus is doing as it projects to V1 is still hard to map onto like where are 3D features coming from because that's normally not discussed. It's normally just
right.
like we
Well,
have this
I
2D
don't,
field of
well, this is the first time I've heard us discussing 3D features, or at least I forgot. Um,
when
again,
we were talking about like motion parallax and or parallax from
oh,
binocular vision and
yeah,
stuff like that.
maybe, yeah.
Because
Again,
yeah, we
it's a
found
good,
some evidence that like at least in mice, they've observed that like motion parallax seems to lead to very early representations of depth
well,
and things like
representation
that.
of depth is not necessarily the same as 3D features, right? A feature is like
Sure.
a sensor patch. The way I've been thinking about it is you take a sensor patch, and if it's got any kind of center surround receptive field, so that could be a part of, a flat area of the retina or the flat area of your skin. Within that patch is if there's any non-uniformity, then you'll have an input. So you can just follow the logic from that. So obviously there's no 3D features on the retina, but I guess we could probably go down a rabbit hole on this for hours here.
Yeah,
But,
yeah. I don't want to
I
distract.
keep coming back on it. I love this idea that you could just think about center surround receptive fields, because if that's true, that sort of answers all these questions. You could just keep going back and say, well, what can I represent with the center surround receptive field? What would make it respond and what would not make it respond? Okay, I probably said enough in this. We haven't let Ramy get to his main point yet.
Okay, so like I said, we just learn the model this way. But my question here is, do we also want to learn? My thinking is that we should not want to learn multiple models for that object at different behaviors. We should not want to build associative connections of the features as they move. Like at every behavioral state, we are not building a new model. And this is my understanding, that we're building just one model of the stapler and then we're applying behaviors to it, but we're not learning multiple models of different behaviors for the same object.
Well, we didn't actually reach a conclusion on this, Ramy. We certainly don't want to learn a new morphological model for every position of the stapler top, right? That would be kind of, we can't, we don't have the time to do that. But on the other hand, we can infer the object in its different positions. We can talk about that. And obviously, if an object has two main positions, maybe it's like always open, always closed, and then move between them, then you might say, yeah, I'll learn the open one and the closed one, and I learned that they move between them. But it seems impractical to try to learn everything in between. This is very much what we were just talking about. In the morphological model, we said, hey, if you got edges where things are, where non-uniformities are occurring, and then you kind of imply that the surface of an object continues even though I'm not sensing it in between. Here it could be the same thing. I have a set of movement vectors. I mean, a set of I'm representing the behavior of this top of the staple moving, and I might be able to generate an image of what the staple should look like at any point along that trajectory, even though I haven't learned it. It's like, yeah, I can fill it in and say, yeah, well, if it's moved this much, this is what it's going to look like. Not that I've learned the morphological model of that.
Okay.
We haven't figured
Yeah.
this all out. So I'm talking as if we understand it all, but we don't understand it all. But these are reasonable assumptions.
Okay.
Yeah, like I think in general, the feeling was kind of it may be somewhere in between where it's like, yeah, we may need to learn some kind of important keyframes almost, but yeah, we don't want to have to like densely sample that space. Yeah.
Okay.
And
Yeah.
we can maybe talk more about like path integration later, because if that comes up, because I think that also is relevant.
The reason I'm bringing this up is that because I think that there's a lot of parallels between learning this and learning the behavior reference frame, and I think that whatever rules we come up with here is going to transfer to the behavior reference frame, and I'll discuss what I mean in a second here. So I'm going to assume here that we don't want to learn this because this is going to be a lot of associative connections. It's like learning a new model for every behavior, a new behavior for every model, and then you have a lot of models. So it's just impractical to do that. So the other side of this is learning movements at locations, and what I want to discuss here is that we're getting patch movements, or not, now it's a feature change, and we're learning it at a location. But we're being anchored here to a behavior, and we want to anchor to this behavior regardless of the object that we're seeing. So we probably, I think we agree on this, that we probably don't want to anchor to a behavior and an object at the same time, because then we get into a combinatorial problem of we will have every behavior has different objects, and then another behavior will have a different object. So it's like we cannot anchor to both at the same time. We have to anchor to a behavior, which means we have to
I mean, we have two separate reference frames, and they can anchor at different times or at the same time, but whether one of them anchors or the other one does shouldn't affect each other, at least in the current setup of the idea.
Sure, but I mean, how does why would we want to have a reference frame that anchors to a behavior at a specific for a specific object? Are we anchoring
We don't. Well, think of it this way. You have the world of behaviors, which is just how things changes relative to each other. And you have a world of objects, which is where features are static relative to each other. And when you first learn a behavior, it's always going to be associated with a particular object. I haven't been able to think of learning a behavior independent of an object.
I agree.
So you're gonna learn someplace, and we can associate a whole behavior with an object, but the behavior has its own reference frame and the object has its own reference frame. But those two, we can associate the behavior ID, let's say, with a location on the object. But now I can apply that behavior to other objects, right? So we don't want the behavior definition is not tied to the particular object, although I can associate it with a particular object. I can say staplers have hinges and refrigerators have hinges and doors have hinges, but water bottles don't have hinges. That kind of thing.
Yeah. This makes sense to me. Would we be able to learn this association from the interaction between the behavior reference frame and the object reference frame? So what we represent in the behavior reference frame is an abstract behavior state, but it's associatively linked to the object in the object reference frame, instead of actually representing relative locations in the behavior reference frame.
It must be associatively linked because when we see the stapler, we know that it can open and close, right? I associate that behavior with the stapler.
Okay.
So there had to be an associative link between the two at some point.
Okay.
But
so-
that doesn't.
Sorry.
No, go ahead.
Go ahead.
Yeah, so the solution we proposed so far doesn't really talk about the associative link. It's basically just to be able to recognize behaviors and recognize objects and recognize them independent of each other. So like Jeff said, they're basically two separate worlds. And if you sense a specific movement, you can recognize that pattern of movements. And if you sense a particular object, you can recognize that pattern of features. But they don't inform each other at all right now in the current proposal. But like Jeff said, we need to be able to do it. But I don't, as far as I remember, we haven't proposed specifically where that would happen if we have an association between object and behavior ID in layer 2, 3, or if we have an association between the two reference frames. So
Right.
Yeah,
We haven't discussed it, but it's obvious it has to happen. It seems obvious to me that has to happen. You know, another possibility that we haven't discussed any of this, as Vivian just said. You know, you might even think of perhaps, I'm just brainstorming here, that a behavior typically is smaller than the object. And perhaps the compositional mechanism could be used for that. You could learn that this object has in some sense, a child behavioral object that is applied at one location and one orientation. So that's another way to do it. You could learn between two regions, two columns. In fact, the more I talk about this, seems pretty good. Two columns and two hierarchical regions, and the behavior is a child of the parent morphology object.
Okay.
Yeah, I think that's interesting. It's kind of like the sub-object behaviors we talked about before with like, yeah, I'm forgetting the exact example we had, but where it kind of breaks off.
Well, yeah, right. But keep going on this idea. The problem, a behavior, first of all, a parent object can have multiple behaviors, right? We talked about staple having a deflection plate behavior, the hinge top behavior. There's other behaviors, adding staples and so on. And each of those behaviors exists at some location and some scale and some orientation to the parent. Well, that's exactly the language we use for compositional objects. So it seems logical to think like, hey, the same mechanism for compositional objects of like the logo on the cup would work for the behavior of the hinge on the stapler. I've said enough about it, but that's a pretty interesting idea.
I completely agree, and I think there's a lot in common in how we learn the compositionality and object behaviors. I think that it's the same learning mechanism, and I tried to talk about it a little bit in the write-up, but I don't think I did a good job. Anyway, so I'm just trying to make comparisons here between learning features at locations and learning movements at locations by saying that in the features at locations, we're anchoring to an object, and we want to represent that object regardless of what behavior it's at. So we don't want to learn multiple models of that. Every model would have a separate behavior. But also in learning movements at locations, we're learning a behavior, we're anchoring to a behavior, and we want to represent that regardless of what model is exhibiting that behavior, because we are anchoring to a behavior. We don't really care what the model is. And this is part of recognizing the behavior. If we want to recognize the behavior regardless of the object that's exhibiting it. And I think it's probably reasonable to assume that how we get there is a different story. How we learn that is a different story. But also, it hints at how I'm thinking about these locations, because I think these locations are somehow associatively linked to physical locations on different objects that have different morphologies. So a laptop top is different from a stapler top. So in my thinking, that a location in the behavior reference frame needs to be linked, associative linked somehow to different physical 3D locations that describe different objects, such that it can apply these movements on them at the same time. And by saying that, it also means that the locations in the behavior reference frame is not necessarily in physical 3D, not necessarily physical 3D locations, because they need to be associated with different objects that have different morphologies in physical space. So,
But aren't they still locally spatial? Like they might anchor at different times to different parts of an object. But if a sensor moves in the behavioral and in the morphology space, like once it's anchored, it would still be the same. Like it would still be kind of moving in 3D space.
I think it starts this way. It's when we're learning, when we first observe a behavior of a stapler opening or closing. I think it starts this way, that we learn it on the stapler. But as the behavior becomes more and more abstract, we move towards a definition of a location in the behavior reference frame that is not tied to the movement. It's tied to moving along the behavior trajectory. What I'm imagining is something like this. I'm saying scale behavior here, but I know we haven't agreed that scale is a behavior, but we're anchored to some behavior, like a scale behavior, and the locations here, these red dots, are basically moving along the trajectory of the behavior. We didn't learn it this way. It became this way. The definition of the location has morphed into this so that it could represent different objects at the same time.
Are you saying that you think that the behaviors aren't learned initially in the behavioral space, but learned in the object's morphology space? Is that what you said? And then later it gets learned in the
It doesn't
behavioral
get
space?
transferred. I'm saying it is learned. It can be learned tied to a stapler morphology in its own reference frame, but the definition of the location in this behavior reference frame will change over time to represent multiple objects. The location
No,
here,
no, wait. Let's be careful there. The behavior, the space of the behavior, I don't think is ever going to change. You can associate the behavior at a particular location on a particular object, but the behavior is defined by its behavioral, by its grid cell space, if you will. Just like an object is defined by its space. That once I know the object, all the points that the object might occupy are defined. So up to now, we've had this sort of like an ironclad rule that once you've at least in grid cells, once you've anchored, you now, the anchoring is synonymous with recognizing the thing. So once I've anchored in the object's morphology space, I know what the object is. And once I've anchored in the behavior space, I know what the behavior is. But but those locations wouldn't change. I mean, that's how we've been thinking about it. If you're suggesting they do change.
It's not that the location changes, but the meaning of the location. So what I'm suggesting here is that at the beginning of learning not scale, maybe let's go to a hinge behavior. At the beginning of learning a hinge behavior, we're learning that behavior is specific to the stapler, and this is how we know how to identify this behavior. It's on the stapler. As we start abstracting it more and more, the location here cannot be represented in physical space in the morphology of the stapler.
Well, let me stop right there, Ramy, because the way we've been viewing it is that imagine you have the definition of an object is static features at position or poses in some reference frame. And the definition of a behavior is changing features at poses in a reference frame. Now, from the very beginning, if I have a changing feature, it's only going to get stored in the behavioral object. And if I have a static feature, it can only get stored in the morphology. They're separated from birth, right? If it's changing, it's going to go into the behavioral space. If it's not changing, it'll go into the object morphology space. So I think that's, if I understood what you said, that's counter to what you were saying.
No, I agree. I just I don't think it's counter. I think what I'm saying is that the behavior reference frame locations need to be abstract enough to represent multiple.
But they are from the start. They're the locations in the behavior space only make sense in the behavior space. They have no actual correlation between they're not tied in any way to the locations in the morphology space.
Or like they're associatively bound probably, but it's not like they, yeah, as you say, it's like a separate
right. The definition of from the very beginning, the behavioral object, the behavioral sequence is its own set of SDR locations, and it never changes.
But
and I think in that, or just kind of from what you were saying earlier, because it feels like in that behavioral space, like having, it's still important that it's like a space, like obviously there's temporal dimension as a complication or whatever, but like you can still move through that space with your sensor, and that affects what you predict. But I agree, we kind of need to be able to, for example, like almost like scale it up or even deform it maybe to apply to different objects. But it feels like that's maybe more about where you bind and also maybe like how large the behavioral space is than it becoming, I don't know, somehow more abstract.
But Niels, that all that gets answered if we take the idea I had a moment ago, which is that behaviors are child objects of larger morphology objects. If they work the exact same way as the logo on the coffee cup, but it's the hinging behavior on the stapler, then we know for the logo on the coffee cup, we have to do a scale and orientation and changing and morphing, and we came up with the answer to that. It was hard, but we came up with the answer to it. So I think that could apply here too. I can say I have a behavior, say hinging, but when I apply it to a particular object, I'm going to do it in the same way I applied the logo to the cup. I'm going to do it. I can do it on a location basis. I can learn those associations as I need to. And therefore the behavioral model can be applied to someplace on a parent morphology model.
Yeah, I really like that idea because, well, first, I mean, we already talked about how behaviors can be recognized at different scales and orientations and locations. But the one thing I was still wondering about was deformations. Like if you imagine the stapler top is kind of curved and moving up and down, you can still recognize that hinge behavior, but it's kind of in different locations. But then Niels reminded me the other day that in a hierarchy, we already have a solution for object deformations. Like we can learn the bent logo by just assigning the logo a location by location basis to the cup and assigning it at different orientations on different locations on the cup. So that would also be a solution for assigning like a bent behavior to an object morphology.
Right. That's exactly what I was saying. Right.
Yeah. I was just putting it in my.
I'm just. You guys may have thought of this. I can't remember if we discussed this now, but I'm just saying yes. That's the same thing. Well, maybe you knew that.
That
was a thread on Slack, so you might have not seen that.
Not in the last few days.
I'm still a little confused about the locations in the behavior reference frame, and so let me ask it in a different way. These locations here, even though they are completely different SDRs because they're in different reference frame, their relative locations, they still, even though we don't store any features or orientations or whatever in this here, but the relative locations between them still in some way defines the shape of a stapler.
No, it doesn't. No, it doesn't.
Well, I guess, yeah, something we've not addressed is maybe that the assumption that movements could be scaled by different amounts in these two reference frames. Or at least,
Well,
yeah, well, actually, I don't think you need that. I think
Well,
you just
but-
need it when you adapt it to a new object, you would scale it.
But wait, let's just go back to what Ramy just said. Ramy, he said that even though they're not, the behavioral model does not represent static features, it still defines the shape of the stapler. I think that's what you said.
Yes.
Okay, I disagree with that. And
Okay.
you could, first of all, the behavioral model wouldn't represent anything that's not moving. So if there's a part of the staple that's not moving, it's not going to say anything about it.
Okay.
You could have a behavioral model, which is just a deflection plate. Okay, that's not going to tell you what a stapler is or what a stapler shape is. It does nothing about that. It just says within this local area, a set of changes can occur, and I can learn that set of changes over time. So it really is a subset
Yep.
of the whole stapler. Just like the logo on the coffee cup is a subset of the coffee cup. It's not the whole coffee cup. It just says
Right.
that. This
No,
point
I
is the
agree.
logo.
I agree. The point is it's still a subset of the locations on the stapler.
Well, at any point, it might be applied to a subset of locations of the stapler, right? It could be applied to your laptop. It could be applied anywhere there's a hinge. So
And that's because these reference frames are synced, and they the relative locations in both the behavior and the object model are the same. Even though it's not store.
well, that's how it's learned. When you're learning it, if you're looking at a physical object and it's exhibiting behaviors, well, sure, but again, think about the stapler. There's a reference frame for the deflection plate behavior, and there's a reference frame for the hinge behavior. Those are completely different reference frames. And at any point in time on a particular stapler, I could apply the reference frame for the deflection plate at some point, and the reference frame for the hinge at another point. But now we have three different reference frames that are really unrelated to each other, only in sense in a particular object are related.
And my point is
And when you recognize them, you can also recognize them in different skill set. Like you might recognize the hinge, learn the hinge on the stapler, but then recognize it in a totally different orientation and scale on a different object, like on the door or on the laptop. So it like when you recognize a behavior on a new object, that reference frame, like how you move through it, might look totally different than how you move through the object's reference frame because you're actually recognizing it at a different orientation, location, and scale.
okay. It's still not clear to me how the
Like,
relative location is similar to the stapler, but we can recognize it on a different object. I know we're still storing movements, but these movements are defined at specific relative locations.
but like maybe if it helps with like a stapler versus a laptop. So when you learn the stapler, yeah, you moved like 5 centimeters or whatever from the kind of hinge point to the tip. And that was what kind of stored that relative movement both in the morphological and in the behavioral model. Now, and the kind of recognition of that behavior is this kind of movement of this hinge type thing. When you're then seeing the laptop open and you saccade to the tip of the laptop that's like moving most quickly is kind of the end, like that's where the kind of hypothesizing the scale of the behavioral model would basically say, oh, okay, I think the behavioral model is actually larger because it's mapping onto this larger object. And so the location, which is the tip of the behavioral model, is going to be bound to the kind of tip of the laptop lid and the corner, which is now separated by a larger distance. And this kind of ties into what we were discussing the other week where Vivian was pointing out we probably want to be able to transform the movements separately for the behavioral and the object models because they may have different rotations and they may have different scales.
Yeah, Yeah. I think it's what you're saying here
if that helps.
makes sense. It is it is useful, or it's not useful, it's necessary that if we haven't seen a hinge behavior before and we learn it on a stapler and we're going to recognize it on an object, that object hinge behavior, it needs to be applied in on a morphology that's kind of close so that we can still anchor to the same behavior. But I think that by anchoring both morphologies, both the both hinge behavior, both the stapler and the laptop to the same behavior, I think this is going to change
You know,
these
it doesn't
locations.
have to be close. Remember, Ramy, at the last retreat, I brought up the example of having a chair where there's a little piece in the back leg that had a hinge on it. There's a totally made up idea. And the chair is nothing like a stapler, you know, and it's only a little part of the chair. So I think you have to just think of these as completely separate objects. The behavior object and a morphology object, the set of each of them, and they can be mixed and matched in different ways. At different locations, different scales, and different orientations.
I think it might be maybe a bit of an issue of like introspection and trying to think of examples where you're applying behaviors to morphologies. I think I get your point of, and I was first thinking like that too, that like, yeah, we're still defining those changes at locations, and those locations tell us a bit about the shape of the object. But I mean, your picture is accurate that the behavior model is just these red arrows at these locations. If I look only at the behavior model, I wouldn't be able to say that this is a stapler. But the fact that they are at these relative locations mean that I will only recognize that behavior if I see changes at those relative locations, and I won't see them on objects that don't have like a solid straight thing that can move like that. So if I'm looking at a ball, I will never recognize the hinge behavior because I can't see these changes on a ball. But is that like
Unless it literally splits in half and basically develops a straight edge that could then map onto it.
yeah.
But yeah, like
Yeah, in
when
that
it's a
case,
solid ball,
I
it's
would
like
see these
right.
changes relative to each other, how they were stored in the behavior model. But if I'm not seeing them, I'm not recognizing them. But it's independent of like the actual object itself. It's just what's physically possible to observe.
Okay, I think I see your point. I just think that yeah, okay, no, never mind.
But do you want to talk a little bit more about the abstract stuff? Because I think we're trying to at least explain how we're currently thinking about it or whatever, but I still don't want to get in the way of you talking about your ideas, because it might build on that in some way, or kind of show us a problem with what we're thinking.
So this is how I was before this conversation. This is what I was going to propose. Basically, is just we anchor to a specific behavior, and the movement becomes abstract enough that the locations here do not represent relative locations on the specific objects, but rather a location in the trajectory of the behavior. So the movement would basically be moving it into an open state or a closed state. I can go on and explain more about this, what I mean here. But.
And is that a space where like a sensor can still move through to make predictions?
It becomes so the sensor will still move. Let me finish the
yeah, please.
These are the end of the slides. These few 4 slides, I think. So I'm just going to contrast behavior reference frame and object reference frame from the way I see it. The object reference frame here on the right, this one anchors to an object, and the behavior reference frame anchors to a behavior. And by saying that, they will anchor to that regardless of the other concepts. So an object reference frame will anchor to an object regardless of what behaviors this object is exhibiting. Like what kind of, like it could be different colors, it could be different states, or scale if we assume that scale is a behavior. And this is a desirable feature. We want to factorize the behavior from the object representation so that we, first of all, we don't build too many associative connections in the object reference frame, but also for recognition. We want to generalize such that we can recognize this object. If I take my stapler and put it under the sun, or if I put it in a dark room, I still want to recognize it. So this is a kind of variability that we want to recognize, that we want to recognize regardless of. For the behavior reference frame, it's this similar idea. We want to anchor to a behavior regardless of what object is exhibiting that behavior. So we need to have this idea of an abstract locations that can represent multiple different objects. They can associate with multiple different objects in physical 3D space, but the location itself in the behavior reference frame is more abstract than that. So this is what I mean here. As we move through, this is probably not a very accurate representation, but as we change the location in the behavior reference frame, we move along the trajectory of the behavior. So this on the right is the object reference frame, and this here on the left is the behavior reference frame. The behavior can change the object. What's in the middle here is kind of like the superposition of both, or like the some sort of a conjunctive code or something like that, kind of like in the Tolman Eichenbaum. It's both of those. In order to actually represent the object at a specific behavior, we need both locations. We need the location from the object reference frame, and we need the location in the behavior reference frame. The behavior does not really represent the object in any physical space. It just represents the behavior, but it can be applied to any object. And then the object reference, the object locations can be applied to that same object, but on multiple different behaviors. So you can change the behavior, but it's changing the behavior doesn't really change your sensor location, for example, like here. On the other side,
sorry. Yeah, no, sorry, I'll let you finish. Yeah.
On the other side, you can change the sensor location, and you can move on. So you can change the sensor location without actually changing the behavior. You can the behavior could be an open stapler, and then you can change the sensor location on it. You're still detecting that it's an open stapler, but you are changing your location on the open stapler like this, or a closed stapler. It doesn't matter, because the sensor movement only controls location changes in the object reference frame. The behavior, the movement of the object controls the location in the behavior reference frame. So you can have movement here, but you don't need to have movement here. The superposition of both, or the associative connections between both, is going to give you finally to be able to predict basically where on the object, given the object and the behavior.
But we still need to move in the behavior reference frame too if we're moving the sensor, so we know where in the behavior model we are, right? So we know what changes to predict at that new location.
If the behavior is not changing, I don't think so. So if it's an open stapler like this, and you're looking at the stapler and you're just moving across the sensor, moving across the object with the sensor, you don't really need to know anything about the behavior except its location in the trajectory of the behavior. I know it's an open stapler like this. I think
what Vivian was saying is that while you're observing the behavior, you actually have to observe the locations that are changing. And there's multiple ones. So your sensor pads can only observe, we'll say, one at a time.
Yeah.
But you need to observe, you have to be able to, if I'm observing a change, I have to know where I am in the space of the behavioral model. And therefore I have to know my location in the behavior model.
That's why we
And that location, yeah, or like where you are in the trajectory space is a function of your location in physical space and your location in time. Because like the stapler is going to be having a different behavior at like towards the end of where it closes, it opens from at the very start. And that's because you're at a different location in that space,
that's
as
what
well
you
as a
showed in
different
your
time.
picture when the sensor movement goes into both of the reference frame and you move through both of them in synchrony using the sensor movement.
I'm sorry, can you repeat that question?
What you showed in your picture on the first slide where you have the sensor movement go into both of the reference frames and you move through both of the reference frames in synchrony.
This one or the very first slide?
The very first slide.
This one?
Yeah, the sensor movement at the bottom that goes into both the objects and the behavior reference frame. And we move, like if the sensor moves, we move in both of the reference frames. Because otherwise, if I have the opening stapler and I saccade from the top to the bottom, I need to make the predictions about those changes that I'm next going to see.
Well, so yeah, this goes back to my assumption here that the location in the reference frame it becomes an abstract look. This location now represents the whole behavior state. So you would know now you have a morphology of the object and you have a location in the behavior reference frame that represents what state it's in. So as you move here, you can predict what the rest of the object will be like because you're learning. This location here it's not at a physical location. It's a location on the trajectory of the behavior rather than.
So you're basically changing from changes at physical locations, and then you change that to actually pooling over all of the changes to define an object state, and then moving through that state space?
Yes.
Why are you discarding the information about the local changes? I mean, how do you still make predictions about local changes if you get rid of that?
You can still make just the way I described it here. This state here is just a behavior state. We have the model, and both of those describe what the actual state of the object is. It's an open stapler or a closed stapler. You can make predictions using the associative connections between the behavior reference frame and the object reference frame. You have it's like a superposition of these two codes or whatever that gives you a full view of what's happening.
So like, for example, like with the stapler opening, imagine as it's opening, there's something occluding your view in between. And then so now you're going to move your eye to where it's no longer going to be occluded. You're going to be able to make a good prediction of what that movement is going to look like at that point. Because that's a location that like, because you're predicting a state, like a location in the behavioral model, but that location is a function of your location in space, which is where you path integrate with your sensor movement. And then you're like, okay, I've learned a feature changes at a particular location.
Yeah. But
so how would you predict something without something like that? I guess
you wouldn't need to. It's just it's the same way when we learn an object model, we're learning features at locations, and we know we can predict what's happening here because we have an object model. When we have a behavior model, we can learn what's going to happen somewhere else because we know how that behavior affects the object.
But how do you know you've
recognize
moved to
them
that
anymore?
location in behavioral state? Like I've made a saccade. How do I know to expect a particular point in behavioral space? I could be anywhere in behavioral space.
No, you're still tracking your behavior, right? right? So
But then this is where like it's occluded. So like I have to make a prediction at like a future point or like a new location.
what exactly is occluded? The object is
The
occluded.
movement of the stapler head.
Of course, if the movement of the stapler head is occluded and you have not anchored to the right behavior, then you cannot predict what's going to look like. If the
And I'm not saying it's occluded the whole time. It's just like I think this was an example Jeff brought up previously where like a stapler is opening, and then let's say at 45 degrees, it starts going behind like a little screen, and then it's going to come out again.
Hmm.
But
So
like
part-
when it comes out again, you don't predict that the stapler head is going like it's going in the kind of exact same like feature movement that was seen, the feature change that was seen at this point in time in space. That's not what you predict at the other end. You predict a new one, which is kind of a function of where it's kind of moved ahead in behavioral space.
you're anchored to a behavior, even though so if I'm looking at can you see my camera?
Yeah.
If I'm looking at this stapler and I occlude part of it and then I still move it, because of the movement that I've seen from the part that is not occluded, I can predict the behavior. I can anchor to the right behavior, and I can predict where am I on the behavior. So that gives me still the full model of what's happening behind the occlusion. You can still predict all of the points behind it because this here represents the behavior state rather than the behavior at the locations, the movement at every location. Maybe I'm not describing it very well. I don't know.
How do you even still recognize behaviors in this solution? Like, where do you store the changes at locations to recognize that there's a hinge behavior going on?
Where do I store the
changes at relative locations that we have in the object's reference frame?
It's the same theory that we already have. It's just that I'm still thinking that the location does not become the relative. These locations will morph, will change to become locations of states, and we can move between these states rather than a location in physical 3D. They don't move by the same way that when the sensor moves, they change the same way. It's not a location like that anymore. It's a location of in the trajectory of the behavior, but it
I
represents.
think I'm a bit confused with like what the states are now doing in the behavior reference frame, because those are not changes anymore. Like when you say it is in a closed state and it's not moving and you're moving on it, that's not like nothing in the behavior model, that because there's no change happening.
No, they still store changes at locations. It's just that, for example, if you've only seen the behavior on the stapler and the laptop, then the location is going to be the full stapler top and the laptop top. It becomes, at this point, becomes the whole top of the object. And then you're storing a movement at this location, which represents the top of the stapler and the top of the laptop. And as you move in the behavior reference frame, it represents the change in the location is just a change in the in the state. Basically, it becomes this change in state.
Ramy, I wonder if all this confusion is coming about because you have maybe a different idea of what we mean by locations, and because sometimes you say physical locations, and nothing in the behavioral model and nothing in the physiology or the morphology model are physical locations. Those locations in those models are both of them are all abstract. It's just relative to each other. And then, of course, an object will appear someplace physically in the world. But I'm just wondering. I'm hearing. I'm trying to figure out what's confusing you, or what the issue you're trying to get at, because I don't see that issue, and I'm just wondering if you have this just a bit different idea what we mean by the space of the morphology. It's not a physical space. It's not like you know, a stapler could have a big stapler, a small stapler, right? I could have it's a set of locations relative to each other. And that's all it is in the morphology model and the behavior model. That's all it is. And after that, they're nearly identical. They're the same process going on everywhere. I'm just trying to, I think we're beating around, I think there's a more fundamental misconception or a difference of opinion about something here. Where you think somehow think the stapler space is more real than the behavioral space. And it's not. They're both equally as real or non-real. They're both as abstract or not abstract, however we want to call them. Is that possible? You're thinking along those lines?
Yes, I'm thinking that they are different. Maybe this is what we need to address.
Right. As I view it, they're not different at all. They're virtually identical. It's just that in one space you're storing the changes, in the other space you're storing static features. So changing features and static features, but after that, they're identical type of spaces. And the fact that you keep saying the word physical space is, I would never use that word, physical space, or very rarely. I have the space of the object, which is, it's really self-referential relative to the object. It's not, when I define a model of an object, it's not physical space. It is model of its stapler space, you know, and it's like all relative to the stapler, but nothing else physical about it. And the same thing with the behavioral model. It's relative to there's a space which is metric, but the different where things are changing in that space is what I'm storing in that model. So I'm just thinking that there might be a more fundamental problem here. Maybe it is. Maybe that is right.
I think So you probably pointed at the problem. My confusion point.
So you know, maybe what this tells me is that, first of all, this is a really hard concept. I mean, these are real. It took me months to understand grid cells. I mean, I read paper after paper. People trying to explain to me. It took me months until I got it. Maybe I'm slow, but it's hard, and the concepts are really hard. And so, you know, maybe what this tells us is we need better we need better way of explaining some of this stuff. I don't know. I'm just saying it could be an education issue.
I think it also, I'm curious because, firstly, these were really nice slides, and I think a nice discussion, and I think helpful for me to also understand better kind of, I think, our current approach. So I'm curious if you kind of go away maybe after today and also just thinking about kind of what we were at least arguing, where you can kind of scale and location by location bind behaviors, that at least in our head right now seems sufficient to do a lot of this. I think it would be helpful if you do identify issues with that, to then bring in concretely kind of then how you see that helping with this, because I think that's also part of the challenge is right now when you describe this, I think we're more seeing it as taking away stuff, like being able to path integrate with the sensor moving and stuff, and it's not clear what it's kind of adding, but maybe there is something that we're kind of missing.
I think one other thing that this maybe highlights, or at least that makes me think that we need to talk a bit more about, is that in the behavior model, there is actually another space besides the reference frame of locations. We have the temporal dimension as well, which is the state space, kind of how if I understand you right, this is maybe a bit like the state space you're describing, where through time we can move through different states of the object. And that's an open question that came up before, if we can actually path integrate through state space. Like if we have a joystick, we know how to go from wherever to wherever in that state space, or if those are discrete sequences and we have to learn a bunch of different sequences that we go through. And then maybe a second related question that I forget if it was maybe you, Scott, or Jose, but when we were talking about the diagram last time and the temporal input going to the behavior model, whether there's also some temporal dimension to the object model, where like maybe what we mentioned earlier, that we can learn certain key states of the object's morphology, like the closed stapler and the open stapler. So yeah, just kind of that, not a topic for right now probably, but that there is actually the second space in the behavior model at least, which is the temporal state space.
Yeah, and which I agree is under kind of visited or under discussed or whatever in the kind of solution so far. Like how, yeah, do we have keyframes in time as well? Like how do we represent that without having, again, like another explosion in how many representations we need? Yeah, one or oh, sorry, Jeff, you're on mute.
Yeah, I'm not too worried about that. I think it's worth exploring. But the behavioral state is pretty sparse, I thought, compared to the object space, the morphology space. And it's only where things are changing, and they don't change forever, and the same location doesn't usually change twice. It's like so I'm not sure about being too dense. I am concerned about how we learn it. Then in our retreat, I kept bringing this up, like how can we learn? I can imagine the final state, behavioral space populated properly, but I don't see how a single sensor patch could learn it. A single sensor patch can't observe all of it at once, So maybe if I could try to, for at least my benefit, summarize several things I've heard here today. First, I've heard that, really smart people like Ramy can perhaps, maybe, I don't want to prejudge this, but maybe you end up with the incorrect idea about what space is. And so we need to address that from an education point of view. Second, I think we came up today for the first time the idea of representing behaviors as children of morphology objects. I don't recall talking about that before, and I think that strikes me as a really great idea. So we should explore that, and that addresses a lot of the issues we're talking about, just as Neil summarized. And then the third thing is we still have this issue of filling in. Like if we have, we can't learn every edge of every surface of a table. We can't learn every part of a face of a cup, and we can't maybe fill in and learn every single point in a behavioral space. We have to be able to fill in between, we have to be able to somehow take the knowledge of what we do have and fill in the consistencies in between. An old idea, but I think we never really fully addressed that. So those are my walkaways so far today. That's just my personal summary.
Yeah, I think that's a nice summary, and also just kind of, two other things I think that came up was like just kind of acknowledging again that we've talked about that we might need to learn like multiple morphology models, at least like maybe a constraint set, but like what is that number? How is that a function of the complexity of an object? And I guess that ties in with the filling in thing you were talking about.
Right, I think it
and
does.
Then and then the temporal dimension. I had a brief thing I wanted to talk about in terms of path integration, unless there was any more in your presentation, Ramy.
No, that's all. Thank you all for the
Okay,
feedback.
cool.
It was really great.
Yeah, thank you. That was really good.
Those are great images, by the way. Really nice presentation.
Thank you.
Yeah.
Very easy to think about things.
Yeah, same. I mean, it's just kind of a silly introspection thing, but we use introspection a lot, and it was just the other day when I was bouldering, you have this concept of when you're looking at the kind of climb. So let me pull up an image that you try and kind of read it. So as in like when you're standing on the ground looking at all these handholds, obviously it's this kind of mess. But rather than just jumping on it and trying to climb it, what you try and do is kind of picture yourself moving through kind of space and actually doing the climb kind of mentally. And I thought it was an interesting example of kind of mentally simulating a behavior, because it's really hard to do well. And in general, you can only do it really over kind of short horizons. And if you're going to do it at all, you have to kind of anchor after a certain kind of horizon and then go from there. So anyways, it just got me kind of thinking that like, and I mean, we've talked about this before, I think, but just like a kind of resolution to this whole question of like path integration versus not path integration is kind of, we probably can path integrate in a lot of behaviors, but only over very short horizons. And I think, I guess, an interesting aspect of this, I think it fits well with the biology of grid cells, which is that I think the more grid cells have been understood, the more they've realized they aren't a very good metric of space over large distances, that they quickly become noisy and distorted and all this kind of stuff, but they're quite good as local metrics of space. And so as long as you kind of don't expect to be able to, in the case of sensor movement, path integrate very far with high accuracy, and maybe also in the case of behavioral movement, move through kind of a behavioral trajectory very far before you kind of reestablish where you are in that, then you can do some path integration, but it's kind of local. And yeah, it might make it easier to learn. Like we've talked about how kind of like in a local space, it's more easy to kind of densely sample it and almost like learn it as like a series of sequences. So yeah, I don't know. If
This is an argument for it being being the temporal aspect being path integratable as well.
Yeah, I think so, but just again over kind of short horizons. So it's like, yeah.
I don't know what it means to be path integral in time. I don't know what that means.
I guess
maybe
yeah,
it's
like
easier
taking
to phrase
different
as
trajectories.
maybe path integratable in state space. So if you
Right.
imagine an object can be in different states, so like the stapler can be open and closed, or in between, but then knowing how to get from one state to another, you observe how it opens, but maybe it's more like it can also move kind of curved to the closed state. So like being able to take a new path to go from one state to another.
Yeah.
It's not really through time, it's more through state
Right.
space.
Okay.
Yeah, because as you say, time is kind of linear.
I mean,
Once you're on the
time-
trajectory of time, you
time-
can't
You can't go
move
backwards
off of
in
it, but
time.
yeah.
We're not getting
or go outside of time.
Right, time travel in the brain.
Yeah, no, I think you're right, Vivian. It's more like behavioral space.
Maybe a better example is like a stick shift in a car. You know the different states it can be in, and you know from every gear how to get into every other gear, even though you maybe in the beginning have never done a specific transition, like maybe you never shifted from gear 1 to gear 6, but you still know how you would get there.
You might have to think about it a bit more, right? Because I think you're second nature going from 1 to 2 to 3, but
yeah, you probably have to think about it, but it's not like you have to have stumbled across it and experienced it to be like, oh yeah, there is a connection between these. You can infer it.
I have one question for you, Nils. When you bouldering, do they have a harness on you?
No.
Oh,
but that's because it's very low down.
Oh yes. Should we allow this behavior? I'm not sure this should be acceptable in the Thousand Range project. We don't want to have,
After
injuries.
we did have a lot of injuries at Numenta, I know.
Right. And I think this is crazy.
They're more hardcore climbers. I can promise you, I'm more of a scaredy cat than Ben and Lucas. So I'm not doing anything too crazy.
One funny side note when you gave that example of kind of scoping out the route is that usually you actually do the physical movement while you're looking at it, or often at least. Like you see people go like this and kind of imagining
For sure.
they go, but they actually do it on the ground, just kind of moving their hands how they're planning to move them. So maybe that's kind of an as well in that process.
Yeah, and I was thinking because in general we're gonna have to get better at dealing with noise as we move Monty into the real world. So like even just path integration in space for morphology models, like we can't assume in the long term that that's noise free. So I was like, you know, is that an issue if we can't do
You know,
like over
it's,
longer distances and stuff? But
I don't, it
but I
shouldn't
think
be
actually,
much.
I think with like no, exactly, and I think with like coarser models, for example, like that would deal with kind of like things like large saccades and
You
stuff.
know,
So
that's what I've used this example many times. So I'm sorry for using it again, but this idea that you're walking in a room at night and it's dark, very quickly as I leave my bed, I can just sense the uncertainty increasing. You know, it's like, oh my God, now I have no idea where I am. But then as soon as you catch a single thing, an edge of a door or something, then you immediately know where you are again. So you can just observe that. You know, it's a very inaccurate, noisy thing over even medium short distances. But I think it's not a problem as long as you're able to re-anchor with a single observation. Um, I think it's
yeah.
something we might want to include
Well,
in
I was going to
models.
say, I don't know if you've heard Jeff, but Ramy's working on some cool stuff with kind of re-anchoring and resampling hypotheses
No, I
at the
haven't.
moment.
Sounds great.
So yeah, that'll
Right,
be, I think, a
right,
nice addition to
right,
Monty.
right. Well, I think, today's discussion for me is like it reinforced, even though Ramy is poking holes in it, I think it reinforced to me the validity of the idea that these two models are really parallel. And now we've introduced the idea that they might be parallel in hierarchy as well. But it's not a hierarchy of behavioral states, it's a hierarchy of a behavioral state on a morphology, which kind of addresses some of the things that Ramy was trying to get at, like how do you apply this to a particular model, a morphology model.
Yeah, that
Um,
also kind of fits with before we talked about like how behaviors would be communicated in a hierarchy. And one of the issues I had with having like hierarchical behaviors is that the behavior model ID isn't really a change anymore. It's like a static feature. So it would make more sense to assign that to the morphology model in the higher levels region. So I think I really like that
right,
idea of using that as a solution for assigning behaviors and kind of being able to deform them and assign them on different locations on an object.
right.
Same way.
It's so interesting because originally we just said, oh, let's apply what we know. So, oh, there must be a hierarchy of behaviors and they're going to work the same way as the hierarchy of morphology models. But it was a very slight twist on that. And I think that's actually a quite good advance for today. That's how it feels
Yeah.
to me.
Yeah.
So however we got there, thank you, Ramy. I think it's a great, it's a great progress.
Great.
Yeah.
Helps.
You can be our foil. You can be out there just poking holes maybe.
Rubber duck.
Yeah.
Well, I thought it was also actually a really nice explanation of where we are so far, the first slides, and a
Right.
really nice visualization. I was actually thinking that this might be a good first video to release if we release this idea, at least the first part of kind of recapping.
I think it was at least helpful to me to go through the basics of the reference frames and also the current theory that we have.
I think we still need to go through the basics again because there seems to be some confusion about it. And I'm not sure what the best way of doing that is. Other than I've said it multiple times. I mean, these are very interesting very challenging conceptual things to absorb. And so that's personal observation about myself. And so we should expect that lots of people are going to have trouble understanding this stuff right from the beginning.
Oh
Yeah, maybe one thing.
I have trouble for sure.
My
hand up.
I think, I don't know if someone should want to do a review of grid cells and grid cell anchoring and so on. That might be useful at some point.
Yeah, and I'm also wondering how much we've talked about kind of how we think about scale, because I know we've had brainstorming sessions on that kind of back in 2022, 2023 when it was just Vivian, me and you, but I don't know how much we've talked about that recently, and so that might be something I don't know if we're taking for granted. Like
Is it
for
unsolved? Well, we have a
I think we have like a reasonable idea of like
right.
like maybe not like the biology is something hand wavy about or like unclear about phase, but at least in terms of like if we were to implement it today in Monty, I think we have a reasonable idea of how we would do it, and it's because it's not that different from rotations.
I would still be interested in going over that again because I think there was actually only one in-depth presentation that Jeff gave about it in like the idea of how it might work in biology, and I was sick that day, so I
Yeah, maybe that would be a good topic
Yeah.
for yeah.
Yeah, it's a pretty simple idea. But you know, I say it's simple because it may not be simple to convey. Well, maybe I'm not prepared to do that today, so maybe we could do it another time.
Yeah, it's also the kind of 6 or sorry, not 6 o'clock, 10 o'clock.
It's time. Yeah, right.
But
So,
but yeah, like I would be happy to, if we did want to do a presentation on that, I'd be happy to talk a bit about how I think it could make sense to integrate into Monty. If you wanted to talk about kind of the biology or something.
yeah, I could talk
But
about
Just one last note. If we do review grid cells and all that, maybe also a couple of slides towards the end about what is our current theory for. I know that we don't have an actual theory for that yet, but how to apply this on abstract space, or what do locations in these.
I had an interesting idea about abstract spaces. And it's really just a half-baked idea. Maybe even less than half-baked. Okay. But it starts with sort of a definition. A definition of what is an abstract space. It's when you are building a model of something that you can't directly observe. So in that regard, V1 or S1 would never build an abstract concept. But V2 could, because V1 is getting an object ID from V1 in terms of the hierarchy, right? We're talking about, compositional structure. And V2 is building a model of its model is based in a physical, it has a reference frame that's updated with physical movement. So again, I'm updating the reference frame with a physical movement, but the things I'm assigning to those locations, some of that information is coming from V1, which is no longer a direct observation. It is an abstraction of what V1 thinks it's learned. V1 says, I think I know what these features together mean, and maybe they represent a letter E. And but then V2 is getting this thing and says, I have no idea what the hell it is that V1's sending me. It's just some SDR. And but I'm going to build models based on it. And so this, I think, was a while back I said I felt that abstraction begins very, very early on in the cortex. And I think this is what I thought of at that time. I couldn't remember it at the time. It needs a lot of fleshing out, but it's sort of marrying two things. One is we might have to have a space and or morphology of a space that is some physical stuff. Like if I'm learning mathematics or physics, I might draw a picture of an atom, or I might draw a timeline, or I might do this or that. So I have to have we talked about this. Are all abstract models based on physical, some sort of physical model? Let's say they are, but the population of the model is stuff that has absolutely nothing to do. Well, it's derived early from someone else. It's like it's no longer an observation of the world. So, the concept of I don't know. I have to come. I don't want to go speculate further. Just let me just let that sit on it for a bit. That abstract models are basically any model where the features are not directly observable in the world, and they had to become from something else. And there needs to be a lot more elaboration on this idea. But it seems like an interesting way of thinking about abstraction.
So in some sense, it comes down to what is the meaning that we assign to locations in that reference frame.
Right. In V1, I'm observing something. There's nothing else that's being assigned to a location in V1 other than something that's coming from the retina. In S1, there's nothing other than something that's coming from your skin. But There could be some exceptions to that, but let's not go there. But as soon as I'm going up the hierarchy and I'm doing compositional structure, now a column is building models of where the features are unknown or already abstracted from the world. They may not be real, or they certainly can't be observable directly, right? I can't observe directly. I don't have a sensor which directly recognizes Ramy. I don't have a Ramy feature detector. You are an abstraction in some sense, based on a lot of other features and other things I'm learning. So anyway, it's just a start going on that path. We immediately jump to like mathematics and physics and quantum physics, how do we understand these things, right? But I think we start with the very basics of, like I described it, and you might be able to work your way up to that understanding. So that's just a food for thought.
Yeah, I like that framing, because I feel like usually when we talk about abstract space, we actually talk about the like location space. So whether we can have non-3D or higher 3D or
Right,
different kind of
right.
space. So like actually defining it by the features is an interesting way of looking at it.
Right.
I guess just to
flips it.
resurface it again, I mean, I'm kind of currently sold on the idea that everything is represented in like 3D or less space. But one idea that I think you presented, Jeff, a while ago was that potentially space could be more generally framed as each mini column learns a one-dimensional movement vector, and then the way you combine them, you can learn different types of spaces
Right.
and how to move through them.
It's a great idea, although I'm not sure it has any validity. So this idea I just presented was kind of going the opposite direction, like you said. It's like going, hey, space itself is not abstract. And I'm not willing to say that.
Wait, and
Okay.
yeah, I also don't know if they need to be incompatible, or like, I feel like abstraction could partly be about the input features and could partly be about
but like
the space.
let's think about the example you use all the time. It's about a family
Democracy.
tree. Well, family
Oh, okay.
tree, right? The
Yeah.
relationship. Well, one way to think about it is that the way you have presented is that there's some space that's actually not physical in any sense, but it's representing the relationships between people. And the other way is saying no. Perhaps it really is just you're drawing a picture of a tree, and that's what we're looking at, and that's our model. And then somehow the abstraction comes about from the features and how they are, and how you do composition in that space. It's a fuzzy idea, but it's touching what I think Vivian was just saying, that maybe space really is always 2 or 3D, and that the abstraction comes about not in the change of the space itself, but in the features and how they're organized hierarchically in them. Anyway, it is past bedtime for you guys.
Yeah.
And I got to get going. So I think there might be a good time to stop. I don't know. Is that all right?
Yeah. No, sounds good.